This lesson is on stoichiometry and it corresponds to the honors chemistry notes for Unit 10. So this is stoichiometry. We are going to make chemical calculations for chemical equations. So when you make something like gasoline or toothpaste, it's important to be able to put things in the right ratios. For example, gasoline is a mixture of different types of fuels in different stoichiometric quantities. If you're making certain combinations for gasoline, you want to make sure that you're making them in the right quantities so that if you run out of one thing, you don't have a whole lot left over of something else. It's just good common sense to only buy what you would need to make the right amount. With toothpaste, also, there's a lot of different ingredients. You want to make sure that, again, you get the right quantities of everything. So that's what stoichiometry is about. It's about getting the right quantities. So by definition, stoichiometry is the calculations of chemical quantities in a chemical reaction. We're going to interpret chemical equations as we do stoichiometry. But first we need to balance the equation. Can you balance this one? A 3 in front of H2 and a 2 in front of NH3. Okay, now that we have it balanced, the equation may be analyzed in terms of moles. So here we have it written out as an equation with moles. We have 1 mole of nitrogen plus 3 moles of hydrogen, because we had a coefficient of 3 up here, yields 2 moles of NH3. Notice for nitrogen we just put 1 mole because there's no coefficient, so we would just always assume that to mean 1. Okay, so we're going to do some simple stoichiometry, just going from mole to mole. So if you think about going from mole to mole, what you want to think about is, that those ratios are based on the coefficients. So in this first example, it says in the equation above, which is the one we just did, so this equation here, how many moles of ammonia are produced when 0.6 moles of nitrogen reacts with hydrogen? So I'm going to go ahead and start with my known. This is going to be similar to the mole map problems where we start with our known. We're going to use dimensional analysis to help us solve. Well, I'm starting with 0.60 moles nitrogen, so I want to make sure that I write that it's nitrogen. Then I want to go to where I need to be. So it says how many moles of ammonia. So I'm going to put a conversion factor, and I'm going to put moles of ammonia on top. And then remember, whatever unit we had here, that unit comes down to the bottom here. So I'm going to put moles of N2 here. Okay, so where do you think these numbers came from? The 2 and the 1. They came from the balanced equation. Remember way back here we had said for every 2 moles of NH3, there's going to be 1 mole of N2 and 3 moles of H2. So we have to go back and use those numbers. In this case, we used for NH3 and for N2. So we want to always multiply what's on top, divide by what's on bottom. So in this case, it's 0.6 times 2 divided by 1. And with proper sig figs, that's 1.2 moles of NH3. My sig figs is going to be based on how many are in the known. Since 0.60 is 2 sig figs, I want 2 in my answer. Here's a second example. See if you can do it on your own first. You might want to pause. Okay, so starting with the known, 7.24. Notice I write out moles of ammonia so that I don't get confused about which substance I'm talking about. Therefore, moles of ammonia comes to the bottom, and it asks in the question to calculate the number of moles of hydrogen. That's why I put moles of hydrogen on top. Again, I look at those coefficients from the balanced equation. It was a 3:2 ratio. Multiply by the top, divide by the 2 on the bottom. I need 3 significant figures, 10.9 moles of hydrogen. Okay, so other stoichiometry problems. On this flow chart, you can get this flowchart from Google Classroom. So if you go to Google Classroom, you'll be able to get to this flowchart. It's under the link for the notes. Basically, we're going to use this stoichiometry diagram as we go through the rest of the problems. What you'll notice is this left side is the known side, this right side is the unknown side. Notice as I go from known to unknown, it's always from mole to mole. And that's where we use the coefficients from our balanced chemical equation. But sometimes we don't start with mole, or we don't want to end with mole. We want to start or end with mass, volume, or represented particles. This should be familiar to you. The mass of 1 mole is the molar mass, or the GFM, from the periodic table. If we're talking about a gas that is at STP, a mole is 22.4 liters. And if we're talking about represented particles such as atoms, ions, formula units, and molecules, we're going to use Avogadro's number, 6.02 times 10 to the 23rd. And we can start with one of these and go to mole, or once we get to the mole of the unknown, we can convert it into one of these. And we're going to use dimensional analysis the whole time. Okay, so here's some examples. How many molecules of oxygen are produced when 29.2 grams of water is decomposed according to the equation? Now, we always start with our known. So I'm going to start with the known, which in this case is 29.2 grams of H2O. Okay, I want to look at my map then. If I'm starting with grams, I'm up here with a mass. And it's asking me how many molecules of oxygen. So I'm going to go to particles for my unknown. So if I follow my map, I'm going to go from mass, which is gram, to mole, to the other mole, and then down here to particles. So my top path follows the map. Remember that from the mole map. Top path follows the map. So I went from grams water to moles water, from moles water to moles oxygen. Notice I didn't just put moles. I'm putting what the moles are of. That way I know, okay, I know something about water in the beginning, so these both say H2O. I want to know something about oxygen, so both of these on this side say O2. From mole to molecule of oxygen. Do you remember the next step? Bottom path follows the top. So whatever unit's up here, I'm going to bring down here. Mole H2O, mole H2O, mole O2, mole O2. Now the numbers are going to come from the map. Grams, I'm going to use my GFM. When I go gram to mole, it's 1 mole. But then the next one where I have mole to mole, then I'm going to use my coefficient. Then when I have particles to mole, I'm going to use 1 mole again. And Avogadro's number for the number of particles. So it was always 1 mole before. It's 1 here, particles for volume, for mass. But when I go mole to mole, that's where I want to make sure that I'm using those coefficients from the balanced chemical equation. So here's an example. Here's gram to mole. It's 1 mole. My GFM for water is 18. That comes from hydrogen and oxygen. So 1 times 2 plus 16 is 18. Over here on the far one, it's 1 mole to 6.02 times 10 to the 23rd molecules. And then in the middle, the only reason I have a 1 in front of oxygen is because there's no coefficient. But then in front of water, there's a 2. So that's why I have excuse me, that's why I have a 2 in front of moles of water. So again, it's only this mole to mole ratio where you might not use 1 in front of mole. Okay, we multiply by everything on top, divide by everything on bottom. So we're going to do 29.2 times 1 divided by 18 times 1 divided by 2 times 6.02 times 10 to the 23rd divided by 1. Of course, we know that we can skip the 1s. Try this out for yourself. but you should end up with 4.88 times 10 to the 23rd molecules, and that's just of oxygen. Again, make sure you pay attention to significant figures. Since there's 3 significant figures in 29.2, you want 3 significant figures down here. Okay, I want you to go ahead and try B, C, and D in your notes before class tomorrow. When you come into class, you can ask questions. These are the answers, though, so you can see if you're right or not. And then if you get stuck, be prepared to ask some specific questions tomorrow in class.